This is a Friday regular secret seminar. It is our great pleasure to have a seminar by Professor Yuki Sato. I think we need some introduction. Professor Sato. He has graduated from Nagoya University, and his main research topic is quantum gravity, and he has written several books and translated some books, and he has visited several institutes, and now he is at Tokuyama College, and at present he is visiting faculty member at Nagoya University. Today he will talk about CDT and what CDT. CDT means causal dynamical triangulation. CDT and Horava-Lifshitz quantum gravity in 2 dimensions. Please.
Hello, thank you very much for a very kind introduction. I'm Yuki Sato. First of all, I would like to thank Muin for inviting me to this wonderful secret seminar. I'm very happy to give a talk. Okay, so today I wish to explain the relation between a lattice model of quantum gravity called CDT and a certain quantum theory called Horava-Lifshitz quantum gravity. In both models in 2 dimensions, 2 space-time dimensions. And this talk will be based on my series of papers. And recently, as a summary, I wrote a chapter of the Handbook of Quantum Gravity, now which is on the arXiv. So if you are interested in some details, please have a look at this paper, this one. Okay. So if you have some questions, please just stop and ask me anytime by unmuting yourself. Okay, here we go. Okay, so this talk is about a lattice model of quantum gravity in 2 dimensions based on dynamical triangulations. Broadly speaking, there are 2 kinds of them. The first one is this Euclidean dynamical triangulations dubbed EDT. So in this EDT, one discretizes the 2-dimensional Euclidean surface, meaning that the signature is the Euclidean by the equilateral triangles, like this. So every single triangle is exactly the same. So, and this triangle serves as a sort of UV ultraviolet cutoff. So thanks to this UV cutoff, you can treat the quantum fluctuations of such geometries non-perturbatively. So this is the EDT. And there is another kind called causal dynamical triangulations, dubbed CDT. CDT is a sort of a Lorentzian version of dynamical triangulations. So in the CDT, one discretizes the Lorentzian geometry with a time foliation, like this picture, based on very special kind of Lorentzian triangles. Also, these triangles are the UV cutoffs. So the important point here is that both in EDT and CDT, the triangle serves as a UV cutoff. So to read off the physical quantities out of these dynamical triangulations, we have to remove the cutoff. This can be done by the procedure called the continuum limit. Through this continuum limit, the discretized surface gets continuous in some sense. And in the EDT case, the resulting quantum theory turns out to be the loop quantum gravity. And this is known to be invariant under the diffeomorphism symmetry. Okay. On the other hand, in the CDT, the resulting quantum theory is not the Liouville quantum gravity, but a certain version of the Horava-Lifshitz quantum gravity. Precisely speaking, a projectable Horava-Lifshitz quantum gravity. And this theory is only invariant under the subgroup of the diffeomorphism symmetry called the foliation preserving diffeomorphisms. So in this sense, both EDT and CDT respectively serve as regularizations for the Liouville quantum gravity and the Horava-Lifshitz quantum gravity. So I think this story is quite interesting. So in this talk in particular, I would focus on the relation between CDT, the lattice model, and the projectable Horava-Lifshitz quantum gravity, which is the continuous theory. Okay. Additionally, in the original CDT does not allow the baby universes and the wormholes to occur. However, it is known that you can generalize this CDT setup in such a way as to include baby universes and wormholes in keeping with the foliation structure. This is the important point. And the baby universe here means the configurations that are pinched off from the parent universe and vanish into the vacuum. So like this picture. And also the wormhole here is a sort of handle that connects the two distant regions of the space-time. So wormhole is a sort of handle in this case. And somewhat amazing thing is that you can treat, you can take in the baby universes and wormholes non-perturbatively in the CDT setup. So it can be computed analytically, and you can take the continuum limit explicitly. So this is the situation. So under this situation, the questions I wish to answer are twofold. The first one is that if we include baby universes and wormholes in the CDT, then what kind of interaction should be introduced to the Horava-Lifshitz case? So this is the one question. And the another one is that does the Coleman mechanism work in this setup? Here the Coleman mechanism was first introduced by Sidney Coleman in 1988, saying that in a given model of quantum gravity, if you sum up all possible wormhole configurations, then the cosmological constant of the model does not important. So this is a sort of Coleman mechanism about the cosmological constant. And I wish to ask whether this Coleman mechanism works or not. And it seems that the answer is yes. Okay. So these are the contents of my talk. I just finished the introduction, and in the next section, I will explain the relation between the lattice model CDT and Horava-Lifshitz quantum gravity by focusing on the quantum Hamiltonian in both models. And in the next section, I wish to explain how to include wormholes and baby universes, which can be done by the sort of field theory called string field theory, or the matrix models. So, by this understanding, in the section 3, I wish to discuss whether the Coleman mechanism works or not in this setup. In the next section, the section 4, when including the wormholes and baby universe in the CDT, and then what happens to the Horava-Lifshitz side? So I wish to explain what happens in the section 4. And in the end, I wish to summarize my talk. Okay. Any questions so far? Maybe no. Okay, so I will move on to the first section. So let me first explain what the CDT is. Okay, the starting point is a globally hyperbolic manifold. So such a manifold allows us to introduce the foliation, global time foliation, like this picture. And each leaf can be considered to be the Cauchy surface. So this means that there is no closed time-like curve. So in this sense, such a Lorentzian geometry is strictly causal in this sense. Okay? And CDT discretize such a foliated space-time based on special kinds of Lorentzian triangles, like these pictures. And the green and blue lines are time-like and space-like edges. This is because if you take the square of the lattice spacing for the space-like edge, you have the positive. On the other hand, if you take the lattice spacing squared for the time-like edge, you have the negative. And this parameter alpha is taken to be positive. It's a certain parameter. Okay, so if you discretize a space-time, foliated space-time based on such kind of triangles, you have this kind of triangulation. Okay, to quantize this space-time, we use the path integral. The path integral of the quantum gravity is that you fix the boundary datas of the initial and the final boundaries. So fix the geometry of the boundaries and take the sum over all possible histories between them. And this can be achieved by the functional integral of with respect to the metric, like this. And in the discrete or the regularized setup, we fix the initial and the final boundary lengths, say L1 and L2. So L1 and L2 are the lengths of the boundaries. And under this situation, we take a sum over all possible histories. And this is achieved by the sum over distinct triangulations. Triangulation is the way to glue the triangles. So if you change the triangulations, you can get the different geometries. So to compute this path integral, we have to specify the lattice action here. And this lattice action is called the Regge action. So let me explain what it is. If you fix the topology of the space-time, yes.
Yeah, question. So the triangle is identical when all the triangles are identical.
Exactly.
Just the direction and then different way of gluing make a different history. Is that
exactly? So you are not allowed to change the lengths of the triangles. Thank you. Okay, so I will continue. So if you fix
excuse me,
yes,
I have also an elementary question.
Yes.
Yeah. Your starting point is Lorentz invariant or covariant action or Lagrangian. But in your introduction, you told us that the resultant action is Horava-Lifshitz type, which is not standard covariant one.
Exactly.
Why is such breaking happens? Usually we impose.
That's an interesting question. Yeah, that's a non-perturbative effect coming from the integral measure. So the action is covariant, but the integral measure is not.
So is it a property of triangulation of your specific triangulation, or it's a general feature of this discretization?
This is a particular to the CDT.
I see.
If you take a different one, say Euclidean dynamical triangulation, you will get the fully covariant quantum gravity.
I see. Thank you.
Algebraic gravity.
Yeah.
Yes. Thank you. But this situation holds at least in 2 dimensions, but in the higher dimensions, we have the much more richer structures. So this is just a 2-dimensional case. Thank you. So the starting action is actually the covariant one, the cosmological constant. And let us discretize this action. So we first replace the UV bare cosmological constant, lambda naught, by the dimensionless parameter divided by the lattice spacing squared. And this integral means the total area of the 2-dimensional surface. In the discrete setup, it is given by the area of each triangle times the number of the triangles. And here, n is the number of the triangles. So this is the Legge action, which is very simple. And then to compute the path integral, usually we perform a rotation to the Euclidean signature. But this can be done very easily. Please look at these 2 equations. And if you replace this alpha by the minus alpha, then you get the Euclidean signature. Okay, so if you do that, this Lorentzian action becomes the Euclidean one, like this. And here, the parameter alpha is not important in the 2 dimensions because it can be removed by the redefinition of the cosmological constant mu. So if you do that, we arrive at the very simple form: cosmological constant times the number of the triangles. So this is the action. So using this action, we can define the path integral of this amplitude. So in 2 dimensions, you can compute this amplitude analytically. So to do that, we usually replace the sum over the triangulations by the sum over the number of the triangles. Here, n is the number of the triangles. So if you replace like this, you will get this entropy factor. So actually, the action is a covariant one, but this entropy factor coming from the integral measure is not. So this carry n counts the number of the triangulations. So this can be computed analytically by combinatorics. So if you perform that, you can obtain the explicit form of this amplitude. But to get the physical quantities, we have to remove the UV cutoff. This can be done by the continuum limit.
Sorry, one more question.
Yes.
Yeah, previous page. So in the, continuous action, I think you neglected Einstein curvature term because it's usually boundary term. Is that correct?
Yes, it is a constant. So
so
I just fixed the topology.
Right.
So if you fix the topology, the Einstein Hebrew term becomes a constant. So I just ignore it.
I see. Okay.
Yeah, thank you. Okay. So so we have to remove the cutoff. So this can be achieved by the continuum limit. So let me explain what it is. So this system has the parameter mu cosmological constant. So if you tune this cosmological constant to its critical value, say mu c, then this summation hits the radius of convergence. So at the critical point, this quantity becomes non-analytic. because of this behavior, when tuning the cosmological constant mu to its critical value mu c, the average number of the triangles blows up to infinity. So this is a very important feature. So tuning the mu to mu c, the average number of the triangles blows up. And simultaneously, if you tune each lattice spacing to 0 in a correlated manner, you will get the continuous surface. So this is the intuitive explanation of the continuum limit. So tuning this mu to mu c, usually one fixes the renormalized cosmological constant, this one. So through this procedure, one can transmute the dimension of the lattice spacing into the physical quantities. Here, the renormalized cosmological constant. So this is a sort of dimensional transmutation. I think it is sort of familiar in the QCD. So if you take this continuum limit, this discretized amplitude, regularized amplitude becomes the renormalized one. And the variables L1, L2, and T here are the continuous variables, okay? And this renormalized amplitude is known to satisfy the differential equation, this one. And this is a sort of Schrödinger equation, and this H naught is the Hamiltonian of this system. And this Hamiltonian is Hermitian with this integral measure. So let me summarize so far. So CDT is a way to discretize the sort of Lorentzian geometry with a foliation. And to remove the cutoff, we have to take the continuum limit. And as a result, the physics can be entirely described by the quantum mechanics of the one-dimensional universe whose length is L that propagates in time based on this Hamiltonian H naught. So the physics can be described by the quantum mechanics. And from now, I wish to quantize a certain version of the Horava-Lifshitz quantum gravity, and exactly we get the same Hamiltonian. Okay, so let's move on to the Horava-Lifshitz case. And the starting point is the 1+1 decomposition of the 2D Lorentzian metric. Let me explain the components appearing in this equation. So we first set up the hypersurface, the blue curve, and there is some time directions sticking out of this hypersurface like this. And the normal and tangential direction to the hypersurface are quantified by the lapse and the shift functions. So the lapse and the shift functions, sorry, and we can, so this H11 is the induced metric on this hypersurface, the spatial metric. So these are the components. And if the theory that we consider is invariant under the diffeomorphism symmetry, then you can change this hypersurface as you wish using the diffeomorphism symmetry. So this means that this hypersurface or the foliation is just a gauge artifact. On the other hand, if the theory is only invariant under the foliation preserving diffeomorphisms, like these transformations, then you cannot change the shape of the hypersurface. So the system has a sort of built-in foliation structure. And Horava-Lifshitz gravity is a field theory and that is designed to be invariant under this foliation preserving diffeomorphisms, FPD. And a two-dimensional case, the action is given by this one. And this K is the trace of the extrinsic curvature. So from this K, one can specify the embedding of the hypersurface. And kappa is the dimensionless gravitational constant, and the eta is a dimensionless parameter. And the lambda tilde here is the cosmological constant of this system. Okay, so this is the sort of two-dimensional Horava-Lifshitz gravity. And in particular, we consider a special version called the projectable case. In the projectable case, the lapse function, this is essentially the time component of the metric, is only a function of time. So this is called the projectable case. And actually, this is a consistent truncation, because if you change this lapse function by the FBD, then the lapse function is still a function of only time. So in this sense, this is a sort of consistent truncation. So to make contact with CDT, we consider this projectable version. Okay. So now we wish to quantize this Horava-Lifshitz gravity. And Horava-Lifshitz gravity is a gravitational theory, and therefore the system is a singular system, meaning that there are some constraints. The momentum constraint and the Hamiltonian constraint. Skipping all the details, but we first solve the momentum constraint. And if you do that, the physics can be entirely described by the gauge invariant quantities, the proper time and the invariant lengths of the one-dimensional universe. And the point here is that this proper time is invariant under this foliation preserving diffeomorphism. Therefore, the proper time is a gauge invariant. And also, we have the invariant lengths of the one-dimensional universe. So if you parameterize this length by the proper time, like this L of sigma, then this length becomes a gauge invariant quantity as well, invariant under the foliation preserving diffeomorphisms. So this can be done just by fixing the lapse function to be 1. Okay, so by this understanding in mind, it makes sense to consider the amplitude of the one-dimensional universe whose length is L that propagates in proper time. Okay, and this can be constructed by the path integral. And so first we set the lapse function to be 1 as a gauge fixing. And to make contact with CDT, we also make a rotation to the Euclidean signature. And then the Euclidean action is very simple, like this. Okay, and this lambda here is the durest cosmological constant. Lambda tilde is the original cosmological constant, and this lambda is actually the lambda of the CDT, as you will see. Okay, so what I wish to do is that from this path integral, we want to read off the quantum Hamiltonian. So usually, to do that, we discretize the time step. So let me show you how to do it. So let's consider a function psi is defined by this. And this psi is some state. This H naught is the quantum Hamiltonian that we wish to know. And epsilon is a very short time interval. And if you expand this function for the small epsilon, you will get the H naught quantum Hamiltonian at the next to the leading order, at the order of the epsilon. So this is what I wanted to do. So to do that, first we insert the completeness relation, this one, unity, right here. So if you do that, this portion can be written like this. And this matrix element underlined with an orange line is the one-step propagator. So this can be expressed by the path integral. So let me rewrite like this. So this quantity can be expressed by the path integral. So if you perform this integral and estimate at the next to the reading order, you can read off the quantum Hamiltonian. And actually, this can be done very easily. I haven't explained about the integral measure so far that appears in the completeness relation, but there are three kinds like this, labeled by A. This A can be 0, plus, minus 1. And this measure can be fixed by some property of the propagators, but I will skip this explanation. But there are three kinds. So depending on these three integral measures, you can find this one-step propagator explicitly by discretizing the path integral. So just plug in this expression into this formula, and you can perform this integral because this is just a Gaussian integral. And then at the next to the reading order, you can read off this H0, the quantum Hamiltonian. So this Hamiltonian has the three orderings depending on the parameter A, the choice of the integral measure. And these are exactly the CDT Hamiltonians. So I just explained the last one when the topology of the one-dimensional space is closed. However, you can also think of the open universe case. In such a case, the CDT Hamiltonian becomes like this. And the middle one is a little bit tricky. Marking the one-dimensional universe, the marking the one-dimensional universe corresponds to introducing some coordinates on the 1D universe. Usually people do this for making the combinatorics easier, but this is just a technical thing. Anyway, all three Hamiltonians obtained in the CDT can be reproduced in the Horava-Lifshitz case once it is quantized. So by this agreement, we can say that CDT can serve as a good regularization for the 2D projectable Horava-Lifshitz quantum gravity. Okay, so now we have the Hamiltonian, quantum Hamiltonian. So let's think about the eigenvalue problem. Just H0 is the Hamiltonian, and we can think of this eigenvalue equation. And interestingly, this system has a discrete energy eigenvalues, discrete set of energy eigenvalues, and square integrable eigenfunctions. So this is nice. And also we can think of the sort of Sato-Hawking wave function. So this is a zero energy eigenfunction, but it is not exactly the eigenfunction because it is not a square integrable. But even though this Sato-Hawking wave function is useful for checking the qualitative behavior of the wave function. Graphically, the Sato-Hawking wave function is a disk. But anyway, now we have a set of square integrable eigenfunctions. Let us estimate the size of the universe using those eigenfunctions. And if you compute the expectation value of the one-dimensional universe, which is given by the cosmological constant. So the size can be completely fixed by the cosmological constant. I think this is reasonable because cosmological constant is the only scale in the system. Okay, and additionally, the wave function decays exponentially when the size of the universe is very large, and its decay is governed by the cosmological constant. So these are the behaviors of the eigenfunctions of the CDT or the projectable Horava-Lifshitz quantum gravity. Okay. So next, I wish to introduce the wormholes in the CDT setup. Any questions so far?
I have one question.
Yes.
Can you explain intuitively why only the projectable theory agree with the CDT? So what about the non-projectable theory? Why you only have a projectable theory in this computation?
Okay, that's very good question, I think. Yes. So the reason to think about the projectable case is that if the lapse function is only function of time, then the two-dimensional field theory can be reduced to one-dimensional quantum mechanics. And the quantities, the proper time, can be gauge invariant. But for the non-projectable case, this proper time depends on the space coordinates, meaning that this is not invariant under the Fourier preserving diffeomorphisms. So to get the sensible one-dimensional quantum mechanics, the projectability is a key. So if you think about the non-projectable case, we cannot reduce the system to the one-dimensional quantum mechanics. On the other hand, we know that the continuum limit of CDT can be described by the quantum mechanics, one-dimensional quantum mechanics.
Right. So, but the question may be why CDT have that kind of thing only?
Well,
I think CDT construction is quite general.
Yes.
Yeah, I see. It's very strange. Yeah.
Sorry, but but this story holds at least in 2 dimensions. For higher dimensional case, there is no strict argument about the relation. But I think it's a very deep question.
Okay, I see. Thank you.
Thank you.
And also, in this construction, the cosmological constant lambda appears inside the square root. So here you cannot consider ADS case.
Yes, we cannot. Yes, that's right.
Okay, thank you.
Thank you. Okay, so now I wish to include wormholes in the CDT setup. To do that, somehow we have to promote the one-body system to a many-body system based on field theory. So this is the string field theory for CDT. And string here means the one-dimensional universe. So first, I introduced the psi-Dagger operator that creates a closed string, the one-dimensional universe, and also introduced the psi that annihilates closed string, one-dimensional universe. And the vacuum is given by these 2 equations. So in the vacuum, there is no one-D universes or strings. And these two operators should satisfy this commutation relation. Okay, so these are the setup for the sort of string field. So using these string fields, you can construct the CDT propagator as I have explained in the previous section. So let us think about this amplitude. So this can be expressed by sandwiching the original one-body Hamiltonian by the operators like this. So this H naught is the one we obtained in the previous slide. So by sandwiching this Hamiltonian, we get the second quantized form of the CDT propagator. But this is exactly the same. So from now, I wish to include wormholes and baby universes in this setup. So to do that, we need to include some interactions. So this is the full Hamiltonian. The first part means the free part, free propagator. And the second one means the 1D universe vanishing into the vacuum. And the third and fourth one are the splitting and joining interactions of the string. And the coupling constant is GS, the string coupling. And this, actually this parameter alpha is introduced to count the number of the genus, but it is not that important. Okay, so based on this full Hamiltonian, in principle, we can compute the following amplitude. So the starting with the M loops that propagates in time and end up with N loops. So graphical like this picture. Okay, but from now, I will focus on the multi-loop correlation function. So meaning that, so we start with the N loops and that propagates in time. And after T goes to infinity, then everything should vanish into the vacuum. So this is the graphical expression for the multi-loop correlation function. So everything should vanish into the vacuum. And this quantity can be computed by the sort of non-perturbative equation called the Dyson-Schwinger equation. The meaning of this equation is that after T goes to infinity, the loops should not evolve anymore. So this is analogous to the Wheeler-DeWitt equation in quantum gravity. Okay, so in principle, if you can solve this Dyson-Schwinger equation, you can compute this multi-loop correlation function, but it is very difficult to solve. However, there is alternate equivalent description based on a matrix model. In the matrix model, there is a non-perturbative equation called the loop equation. And this loop equation is exactly equivalent to the Dyson-Schwinger equation in the string field theory. This is true if parameter alpha in the string field theory is equivalent to the 1 over n squared. N is the size of the matrix. And alpha appeared in this merging interaction. So essentially, this parameter alpha counts the number of the genus or number of the wormholes. Okay, that is why this parameter alpha is related to the matrix size n. But anyway, the corresponding matrix model is given by this, and this M is the n by n Hermitian matrix. So this is very simple matrix. And so from now, I wish to take a sum over all possible wormholes up to infinity using this matrix model. But if you wish to sum up all possible wormholes, you can simply set this alpha to be 1. because we don't have to count the number of the genus. So if you set this alpha to be 1, this means that the size of the matrix is equivalent to 1. So the matrix integral can be reduced to the one-dimensional integral. So the great simplification happens here. So thanks to this simplification, we can compute the multi-loop correlation function non-perturbatively. This includes all possible wormhole contributions. So this can be essentially expressed by the Airy functions. And this C is the string coupling constant measured by the cosmological constant. So this is dimensionless. And from this expression, you can learn a sort of interesting thing. This multi-loop correlation function can be expressed solely by the single loop function. Okay, but and then, so among these, I just focus on the single loop function, which is the Hartle-Hawking wave function. So graphically written like this, but this wave function includes all possible configurations of the wormholes and the baby universes non-perturbatively. And this is expressed by the Airy function. So although this is a non-perturbative expression, we can do the asymptotic expansion for the small string coupling constant. And if you do that, you can see the exponential decay. So this happens for any finite order of perturbation. So this is a very important point. For any finite order of perturbation, you can see this exponential decay. Okay. So let me plot the Hartle-Hawking wave functions. So the vertical axis is the Hartle-Hawking wave function, and the blue one is the wave function including all possible wormhole effects. So expressed by the Airy function. And the red one is the Hartle-Hawking wave function for the original CDT, meaning that there is no wormholes at all. And the horizontal axis is the size of the 1D universe. Okay. So when the size of the universe is very small, the behavior of the wave function is very close to that of the original Hartle-Hawking function without wormholes. So it decays exponentially, and its behavior is governed by the cosmological constant. However, once the size of the universe becomes big enough, it starts oscillating like this. And this behavior is governed by the string coupling constant instead of the cosmological constant. This drastic change of the behavior should be caused by the infinitely many wormholes. This is because at any finite order of perturbations, you can see the exponential decay. So such an oscillating behavior should be caused by the infinitely many wormholes. Okay, this is the behavior. And next I wish to do is to find out the quantum Hamiltonian that includes the contributions from the wormholes. So when there is no wormhole, we have this equation. H naught is the original CDT Hamiltonian, and this W naught is the Hartle-Hawking wave function. So this is essentially the Willard-Wade equation. And then, if we include infinitely many wormholes non-perturbatively, we know this Hartle-Hawking function, which is expressed by the Airy function. And we wish to determine this H, this Hamiltonian. Yeah. This is possible by the following two conditions. First, this Hartree-Hawking function should satisfy the Airy differential equation. Okay, this is because this W is expressed by the Airy function. And the second condition is that if you turn off the string coupling constant, the Hamiltonian should coincide with this H naught. H naught is the Hamiltonian without wormholes. So by these two conditions, you can fix the Hamiltonian. This is very simple one. So the point here is that this is the one body Hamiltonian. It is not the many body Hamiltonian of the many body system. This is just the one body Hamiltonian. However, this Hamiltonian includes all the contributions from the wormholes and baby universes. It is expressed by this last term, L squared. So you might think this is problematic because of this last term, the potential is not bounded from below. However, this is a very special case called classical incomplete. I don't have time to explain details, but if the system is classical incomplete, we can say the very great thing. So even though this potential is unbounded from below, you can get a discrete energy spectrum and the square integrable eigenfunctions. So, so if you are interested in, I would recommend you to read the second paper. Okay, so anyway, now we have a set of square integrable eigenfunctions. So this is good. So using these eigenfunctions, we can estimate the size of the universe. Remember that when there is no wormhole, the size is completely fixed by the cosmological constant. However, once you include infinitely many wormholes, the size becomes extremely big, and it is not controlled by the cosmological constant. So, so this is the sort of behavior. Okay, so far I have explained how to include wormholes non-perturbatively based on a matrix model or the string field theory. Anyway, as a result, we get this effective Hamiltonian. This Hamiltonian is the one-body Hamiltonian, but includes all possible wormhole effects. And it is expressed by the last term. And so from now, I will explain this behavior can be seen from a quite different point of view. So let's go back to the original path integral of the CDT. So there is no wormhole at all. Graphically, we think about this amplitude, free amplitude. And the action, the Euclidean action is given by this one. And here, this lambda is just a constant. It's a cosmological constant. However, if this lambda is not a constant, if this lambda is not a constant, but fluctuates in time following the Gaussian distribution, let me think about this case. So this can be expressed by the path integral. So the cosmological constant lambda fluctuates by the field mu, and this mu follows the Gaussian distribution. And since this mu is a Gaussian, you can perform this integral explicitly. So if you do that, you get this action, effective action, sort of. And as we have done before, to read off the quantum Hamiltonian from this path integral, you have to discretize the time step. And if you do that, you can read off the quantum Hamiltonian. So this is exactly the same as the one obtained in the previous slide. Okay, so this means that if there is no wormhole at all, and if you think that the cosmological constant fluctuates in time, and then such a behavior can be reconstructed by the sum of the all possible wormholes. So this is quite an interesting relation, I think. Okay. So this is my last section. So far, I have explained how to include the wormholes and baby universes in the CDT setup. But what happens to the Horava-Lifshitz side once you include such effect? Okay, so in the Horava-Lifshitz case, let us consider this action. The first one is nothing but the action for the projectable Horava-Lifshitz gravity. And the second one is a new one. This is a sort of bilocal interaction term. This term means a wormhole that connects to distant points in the space-time at equal time. So this is the wormhole bilocal interaction, sort of. And actually this weird-looking interaction is allowed because this is invariant under the FPD, foliation preserving diffeomorphisms. So it is possible to include. So if you quantize this sort of effective theory as before, we get the quantum Hamiltonian. So again, this is exactly the same as the one including all possible wormholes in CDT. And this GS, if this coupling constant beta is equivalent to the string coupling constant. So in the Horava-Lifshitz case, we can just simply include bilocal interaction to include all possible wormhole effects. Okay, so let me summarize my talk. So in the first part, I have explained the relation between the lattice model, CDT, and the continuum theory, the projectable Horava-Lifshitz gravity in two space-time dimensions. And then I have shown that the system can be expressed by the quantum mechanics of the one-dimensional universe. And in the next part, I have explained how to include wormholes and baby universes. And in this setup, we can compute the Hartle-Hawking wave function. And the behavior looks like this. And when the size of the universe is very small, then the wave function is very close to that of the wave function without wormholes. So it decays exponentially. And this decay is governed by the cosmological constant. However, once the size of the universe becomes big enough, then it starts oscillating. And its behavior is governed by the string coupling constant. And also we have a set of square integrable eigenfunctions. And if we, by using these eigenfunctions, we can estimate the size of the universe. When there is no wormhole at all, the size is fixed by the cosmological constant. On the other hand, if you include infinitely many wormholes, the size becomes extremely big, and it cannot be governed by the cosmological constant. Okay, by these two behaviors, we can conclude that a sort of a Coleman mechanism works in this case, meaning that the large universe is independent of the cosmological constant. And we also have shown that if you think about the cosmological constant, it's not a constant but fluctuates in time, then such effect can be expressed by the sum over the all possible wormholes. So this connection looks very interesting, I think. And there is one ongoing study. So we have learned from these studies that this sort of fluctuating behavior, oscillating behavior of the Hartle-Hawking wave function is caused by the infinitely many wormholes. So then what kind of infinitely, well, say infinite genus surface is important in this case? This is one interesting mathematical question. And also, there is another paper, other papers relating to the studies. So this kind of changing behavior of the Hartle-Hawking wave function can be seen in a different model, say the non-critical string theory. Precisely speaking, C equals 1 Liouville theory. So if you are interested in, I would recommend you to read this paper, the first papers, and also this old paper is also interesting. Okay, I think its time is up. So thank you very much.
Okay, we would like to thank speaker. Any questions or comments?
Yeah, I have one question. So,
Yes.
so I mean, what about the situation in the, for example, 3-dimension or 4-dimension? Okay. So I saw some 3-dimension and similar analysis by colleagues and others. So do you have any some comment about that? So, I mean, the question is whether, what about this, for example, 3-dimension generalization of this work? Is it possible?
Sorry, I think your voice is cutting. Could you?
Yeah. So the question is whether 3-dimension generalization is possible or not in this CDT theory.
In higher dimensions.
Yeah.
Okay. Yes, that's a very interesting but difficult question. So there are some studies, for instance, in 3 dimensions, the model called locally causal dynamical triangulations was proposed. In such models, you do not allow the foliation. You just respect the local causality. And then if you perform such locally causal dynamical triangulation simulations, if you do some simulations, you will see the similar behavior as obtained in the CDT simulations. So in this sense, we can think that the foliation is not that important in the CDT. So if it is true, in the higher dimensions, you cannot see any connection to the Horava-Lifshitz gravity. But there is counterexample based on some Landau theory technique. In the 3 dimensions, you can see the similar behavior. So, well, it's a bit difficult to explain, but in the 3 dimensions, if you use the sort of Landau field theory technique, you can see some connection to the 3-dimensional CDT and the 3-dimensional Horava-Lifshitz, or the theory with theory invariant under the foliation preserving diffeomorphisms. So there are some studies, but it is quite difficult to determine the relation because we cannot perform the analytic computations for higher dimensional CDT. That's the That's the main reason.
But several years ago, I saw a paper by Khalid and Horava and others about some simulation in CDT projectable theory. But have you looked at it, and do you have any comment about that?
I think there are several papers on which one.
Khalid and Horava and others.
So I think the one they discretized the Horava-Lifshitz theory based on CDT. Is that correct? I think it is just a discretization of the Horava-Lifshitz based on the CDT. So
so they did also some simulation about the cosmology. Like your work. So, yeah. But they also consider only the projectable case. But I think in principle you can also non-projectable case. So I don't know whether
okay. I think the proper time, the time is a sort of gauge invariant in the CDT case. If you want to do that, I think the projectability is very important. Because if you think of the non-projectable case, the proper time is not a gauge invariant because it is a function of space. So
another question is actually, for two-dimensional gravity, so rather than just Einstein gravity, you can also consider scalar coupled theories, so-called 좌표를 타입해버린 model. So I think it is still, possible to realize that gravity in your setup. So what is the right thing?
In the continuum case,
yeah. So basically, I think you only consider Einstein gravity.
Yes. In 2D CDT,
right,
yes.
Right.
Yes. Yes. There are some examples for matter coupling. So you can include, for instance, the Ising spins in the 2 dimensions, but it cannot be solved analytically, but you can perform some simulations. And the result is that, but basically if you include Ising spins, it becomes the fermions in the continuum limit. But simulation says that the interactions among fermions and geometry is extremely weak. So they are essentially decoupled in 2D CDT. On the other hand, in the Euclidean case, it is strongly coupled. And the back reaction of the geometry to the matter is extremely high. It is characterized by some KPZ exponent, but in the CDT case, the fluctuation of the geometry is relatively weak. And but there is another case coupling to the gauge fields, Yang-Mills field. In that case, the model can be solved analytically, and we know the result. But the scalar field, when Well, so if you want to couple the scalar field, I think it cannot be solved analytically, and there is no paper about that.
Mm-hmm. That's true. Yeah. Okay. Thank you. Thank you very much.
Thank you very much.
I have one final question. In your final Horava-Lifshitz action, you
Yes.
showed us an bilocal interaction term.
Yes.
Then, does that mean we can construct traversable wormholes?
Traversable.
Wormholes.
Yeah, simply the wormhole. To make it traversable, we need some negative energy stuff. So, well, I'm not sure if it's. So you were talking about the classical traversable wormhole solution in this setup. Is that correct?
Well, I'm just asking. Bilocal interaction is non-local interaction, so
Yes.
it can So it can create non-local something.
Yes, non-local.
So
Yeah, but
does it mean the traversability in some sense?
Traverse, but okay. Okay. So this one. Okay. So this is a bilocal interaction connecting the two distant points in the space-time, but at equal time slice. So I think it is not traversable in this sense. But this is sort of effective wormhole interaction. Well, this kind of term can be induced if you're looking at the wormholes from the very distant region.
So you showed us that the Hamiltonian can be negative because of that term. Is it right? Minus GSL square.
Yes, that's correct. Yes.
Yes. So it seems to be related to the transversibility, as you told us that negative energy.
Well, but yeah, but it is not directly related to the traversable wormholes. So in a traversable wormhole, you have a classical wormhole solution, and you have to add matter term whose energy is negative. Then somehow such a metric can be traversable, meaning that one can remove the real singularity of the black hole. But yes, but naively, I think this negative potential may not be related to the traversability, but I see, but maybe related. But sorry, I can't answer that question. But yes, it is true that this contribution produced the negative energy, negative potential. That is true.
Thank you.
Thank you.
Other questions or comments? Okay, if there is no more question, let's thank speaker again.
Thank you very much.
Okay, let's finish the formal part, and
Okay.
Professor Muin Park can continue. Please go ahead.
Just a second. Yeah, thank you very much for your, nice explanation. Actually, I'm interested about some higher dimension generalization, but
Yes.
yeah, but I think it is not quite easy.
Yes. But there is a very nice paper by Benedetti Dario.
Mm.
He is discussing the connection to the Horava-Lifshitz in 3 dimensions.
I see. So in CDT formulation.
Yes.
I see. Okay, so please send the reference
Yes.
later.
Yes.
Regarding the non-local term, I think that Sang already asked about that. So this is what this looks like the term in the user traversable wormhole in the string side. Do you familiar with that? So
Well, but I think the by local term it's just a effective wormhole interaction term first introduced by Hawking.
Really? Oh.
Yes.
I didn't know that. I see. Then I think this term can be also considered in higher dimension also.
Yes, that's true. Yes, that's possible. Yes.
Right, but I think this term has never been considered in the higher dimension algebra. Yeah.
Yeah, I'm not sure what happens if you include such local terms into the higher dimension of the Lifshitz.
Right. So here, the regarding the eta parameter here.
Yes.
Right. The surprising thing is that when eta goes to 1, it is just a GR limit, so it disappears. This term disappears.
Yes.
Right. But your result seems to show that the eta is non-zero and not 1.
Yes, cannot be.
Yeah.
Yes.
Yeah. And also, in your CDT setup, I think you only consider cosmological constant term without this kind of term, right?
In the CDT.
Yeah.
Yes.
But
yes.
Yeah, but this Horava-Lifshitz should have this term. So I think
yes,
you might miss one term in the CDT. No?
So yes, exactly. So in the CDT, we have only the cosmological constant term, and there is no kinetic term. But such kinetic term can be induced from the integral measure of the path integral.
So you can actually reproduce exactly?
Yes. You can check explicitly. So the kinetic term, sorry. So this one, so carry n just counts the number of the triangulations. So from this part, you can get the kinetic term.
So in a certain sense, kinetic term is quantum mechanically induced.
So the action is very trivial, but the non-perturbative effects are very non-trivial.
So, in the context of Horava-Lifshitz, so kinetic term is not the surface term anymore when lambda is not 1. Right. Yeah, I see. Thank you very much for your interesting talk. So I mean, I want to contact you again about the further question.
Yeah.
Okay.
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 Thank you for
Thank
inviting
you.
me.
Yeah. Have a nice
Yeah.
day.
Thank you.
Okay. Bye.
Bye. Maybe should I stop?